Hi, welcome back to another episode of Algebra in Words, the video series on YouTube. In this video, we're going to continue our discussion on radical expressions. Specifically in this video, we're going to be looking at simplifying and combining radical expressions that come in various forms. And if you want to follow along with what we're about to do in written form, you can follow along with these methods in my book, Algebra in Words 2, and I start that on page 60. The link to that, to Amazon, is in the description box below. So let's get started. Basically in this video, we're going to be looking at three things. We're going to be looking at how to simplify what's known as a non-perfect root, meaning as opposed to a perfect root. I'll explain that in a second. We're going to be looking at the product rule of radicals as well as the quotient rule for radicals. So what do I mean by simplifying a non-perfect root? Well, for example, a perfect root or a perfect square, for example, would be something like 9, because the square root of 9 is 3, or plus or minus 3. But more specifically, a perfect root, or for example, a perfect square would be a number that when you take the root of it, it gives you a non-decimal number. So what we're going to be looking at here is looking at how to simplify radicals in which the radicand, or the number, is not a perfect square or a perfect root, and I'll show you how to factor that. We'll do that in a second. The product rule for radicals means when you're multiplying multiple radicals together that have the same root, you can combine them under the same radicand with the same root by multiplying their radicands together under one radical symbol. And likewise, the quotient rule for radicals is sort of the same thing, but for dividing. If you're dividing one radical by another, and the radicals are of the same root, you can combine them under the same radical symbol as well by dividing their respective radicands. So I'm going to erase these little bullet points and put examples on the board so that we can see them in action. So let's start with the first three examples that I have on the board. The first one is an easy one. It's the square root of 3 times the square root of 3. We're going to apply the product rule to that. And so when can we apply the product rule is the first question. We can apply the product rule when you're multiplying radicals with the same root. And don't you agree that this is the same root as this? They're both the square root. They happen to have the same radicand, 3, but that's kind of immaterial here. So to apply the product rule, we're going to multiply the radicands under the same root. So it's going to look like the square root of 3 times 3. And then we can further multiply that. That's 9. And then we're going to complete the final evaluation by taking the square root of 9, which is 3 or plus or minus 3. So that was just a basic run-through of the product rule. We're going to do the middle one last. Let's look at the bottom one next, because again we're going to be applying the product rule. And it's the cube root of negative 2 times the cube root of negative 4. The first question you have to ask is, are the roots the same? And in this case, again, yes, they are. They have the common root 3. Therefore, we can apply the product rule by multiplying the radicands of each under the same radical like this. And we have the cube root of negative 2 times negative 4. That's pretty easy. And then we're going to multiply them to get positive 8. The cube root of positive 8. And finally, you can now evaluate this by taking the cube root of 8, which is a perfect cube. The cube root of 8 is 2. And that's once again just another example of the product rule. So now let's look at the middle one. And just so that we have some space, I'm going to erase the bottom one. Okay, so let's look at the bottom one, and I chose this one for a specific reason because you probably noticed that we are going to utilize the product rule here. However, we are also going to utilize simplifying the square root of 18 in this case, and that's the reason I chose this. So if we look at the square root of 2, can that be any further simplified? No. And when it can't, leave it as the radical form, meaning there's no need to take the radical of it on the calculator and convert it to a decimal. Leaving it in its radical form is actually its most perfect form and the form that it's most easy for us to use. So anyway, leave square root of 2 as square root of 2. But now we're going to look at the square root of 18. And let's just focus on that for a minute. This is to teach you how to simplify a non-perfect radical. Now if you look at 18, do you agree that it's not in its prime, that 18 is not a prime number? Yes. But unlike when you prime factorize a number, simplifying radicands and radicals is a little bit different. And this is very important, what I'm about to tell you. What you want to do is to try to factor it into any perfect roots, in this case, any perfect square factors, and then any other factors that are left over. And you're going to split them apart. So what I want you to think about is, think about just factors of 18. There's 2, there's 3, there's 6, there's 9, right? And of course there's 1 in 18. Of those numbers, are any of those perfect squares? Hopefully you think to yourself, 9 is a perfect square factor of 18. So that's how we're going to split the 18 up. So now, just under the same radical, we're going to write 2 times 9. But now in the next step, at least intermediate step, we're now going to sort of do the reverse product rule. Meaning, if you think of this one, we had 2 radicals, and we combined them under the same radical and evaluated. But you can do the reverse. You can factor a number into factors like this, and then break these up into separate factors, separate radicals. So it's actually going to look like this. Where this now became the square root of 2 times the square root of 9. And why do we do that? We do that, well, because we can, but also if there's a factor that's a perfect square, we can then evaluate that, meaning getting rid of the radical. So in other words, the square root of 9 is 3, and we're going to convert this to 3, and that's going to come out as a coefficient in the front of whatever factors remain. Now the remaining factors here are square root of 2 and square root of 2, and now we're actually going to apply the product rule to these two and combine them to be the square root of 2 times the square root of 2 as the square root of 4. And now the square root of 4 happens to be a perfect square, and we're going to evaluate that as the square root of 4 is 2. So let's just bring the coefficient 3 down, and bring down the square root of 4 as 2 down. And now we have 3 times 2, we can multiply to get 6. So the final answer to this example is 6. Now, in case you're wondering, could we have applied the product rule in the very beginning to do the square root of 2 times the square root of 18 as the square root of 36? And the answer is definitely yes. And truthfully, it would have been faster had we done it this way. Notice, we would have gotten the same answer. I should have said plus or minus 3 and plus or minus 6 for this, and this would be plus or minus 6. But the point is, we would have gotten the same answer, and there's multiple ways to do it. I specifically chose this way because I wanted to show an example of how to simplify a non-perfect root radical first, and this just gave me the opportunity to do that. So So I'm going to pause the video and put a couple more problems on the board. I have 2 more problems on the board. Let's start with the one on the top. It's the square root of 5/3 times the square root of 1/3. We're going to start by applying the product rule and multiplying them under the same radical because their roots are the same, they're square roots. So I'm not going to write every intermediate step now because I think you got the hang of it from a couple minutes ago. But what is 5/3 times 1/3? It's 5/3. It's actually 5/9. Multiply the numerators across, multiply the denominators, and get 9. Now, if you look at the 5 and the 9, you probably notice that the 5 is not a perfect square, but the 9 is. That's fine. Now we're going to apply the quotient rule here. And the quotient rule, one way of looking at it is when you have one radical over another radical, you can combine them under the same radical. Kind of like this. But in this case, we can also do the reverse if it suits our situation. And in this case, it does. So I'm going to break this up into the square root of 5 times the square root of 9. And why does that help here? It's because, as we just said, the square root of 5 is not a perfect square, but the square root of 9 is. So for the non-perfect squares, can we simplify or factor the 5 down anymore? No, it's already in its most prime factorized form, so we're going to leave it square root of 5. But the square root of 9 can be taken as plus or minus 3. So I'm going to write 3, and I'm just going to write the plus or minus in the front of the fraction. Plus or minus the square root of 5/3. So that's all there is to that problem. We applied the product rule first, and then we sort of did the reverse quotient rule by breaking apart the numerator and denominator so that we could evaluate the denominator, which you could take the square root of, and then since the top portion we could not take the square root of it, we just left it in radical form. Let's look at the bottom, and you're going to notice we have a similar situation. So the first thing we want to ask ourselves is, can we simplify the fraction under the radical first? 16x over 81. 16x over 81. And the answer is no. So we're going to proceed to the next steps. Now the next thing that we're going to want to do is to, let's split this up, and I'll show you why we're going to split it up. It might stand out to you that 16 is a perfect power of 4, and 81 is a perfect power of 4. But the x is not, and that's going to be what we have to kind of take into account here. So that's fine. We're going to use the reverse quotient rule by splitting this up into the 4th root of 16x in the top and the 4th root of 81 in the bottom. Now, just looking at the top, because we know that 16 is a perfect 4th power of something, but x is not, we're going to now use the reverse product rule to split that up into the 4th root of 16 times the 4th root of x, and I'm just going to rewrite the bottom. And now we're going to evaluate any portions that we can. The 4th root of 16 is 2, and we should say plus or minus 2 because that's an even root. So plus or minus 2. Now x is just x. We cannot further evaluate that or break that down. We're going to leave that 4th root of x. And in the denominator, 81 is a perfect power of 3, so the 4th root of 81 is 3. We would normally say plus or minus 3, but we already have the plus or minus, so it would just be redundant to do it again. So the answer comes out to plus or minus 2, the 4th root of x, over 3. So I'm going to pause this and put a couple more problems up. I have two final problems on the board. Let's start with the top one. It's the square root of 72. And this problem is, again, just one isolated problem where we're going to try to simplify the square root of 72 as much as possible. We did that a little bit in one of the previous examples, but in this one, we can just focus on that. So if you remember, the way that you want to do that is by looking at the radicand and factoring it and trying to find any perfect root factors. Since this is the square root, you should be thinking of all perfect square factors of 72. Now, if you broke that up, you might think of 9 times 8, and you might even break that down into 9 times maybe 4 times 2, where the 9 and the 4 are perfect squares. But you could also, if you actually multiply the 9 and the 4, the 9 and the 4, then actually the best way to think of this is 72 is the product of 36 times 2. And why did we choose these factors? Because 36 is a perfect square, and 2 is not. So again, we broke it up into the perfect square factors and whatever else is left. And that being said, the reason we do that is so that we can apply the reverse product rule and break this up into the perfect square radical times the non-perfect square radical. Then you can take the perfect square of the 36 as plus or minus 6 and leave the remaining radical as is. Plus or minus the square root of 2. And once you get comfortable enough with this, you may not need to actually show the step where you're breaking it up from this into this. You could basically, once you kind of know what your end goal is in mind, is to just go from this step to this step. Take the square root of the 36 as plus or minus 6 or whatever the perfect square is, and leave the remaining non-perfect root as whatever it is. Just remember to bring them all over to the end. Okay, and then I have a slightly more complicated one as our last problem for this video. It's the cube root of negative 81 a to the 5th b squared. And in this one, we're going to be using a couple different principles from before. One principle is basically the reverse product rule of radicals, meaning we're going to be able to split this up into individual radicals. But basically, we're going to be doing like from this step to this step. So I'm probably not going to show that. But what we're also going to be needing to utilize is the product rule for exponents with a common base. And I'll show you how we're going to do that in a second. So the first thing is, let's focus strictly on the negative 81. And I want to focus on thinking of how to factor that into any perfect cube factors. So the perfect cube factor for negative 81 is going to be negative 27, that's the perfect cube factor, times 3, because 27 times 3 is 81. This is the perfect cube factor. This is the non-perfect cube factor. And I left the negative with the 27. It doesn't really matter which factor you leave it with, but I left it with that because we're going to factor that out. Now let's focus on the a's. We have a to the 5th. Is a to the 5th a perfect cube? No, it's not. But are there any perfect cube factors within there? That's why I said we're going to be utilizing our product rule for exponents here, kind of the reverse of that, because how can we split up a to the 5th into any perfect cube factors and then the remaining factors? It's easy. Subtract out multiples of 3 from the 5. So for example, if we split a to the 5th into a cubed times a squared, it equals the same thing, because if we were to apply the product rule for exponents, and we multiply common bases with exponents, we add their exponents. 3 plus 2 is 5, and likewise you can split up the 5 into 3 times 2. So that's why we're utilizing that rule here. And then finally, what about the b squared? Well, we would try to do the same thing if it were higher than 3, but it's not. So basically we're going to leave b2 as b squared. And now, starting from left to right under the radical, we're going to evaluate any perfect cubes and leave whatever is not a perfect cube, we'll leave that remaining under the radical. So let's start from left to right. And the cube root of negative 27 is negative 3. So that comes out. The cube root of 3 is going to stay the cube root of 3, like this. And notice I left a little room here so that we could put any other factors that we need to. Now what about a cubed? Well, a cubed, that's why we split this up into a cubed times a squared, because a cubed is a perfect cube, and the cube root of a cubed is a. That's going to come out of the radical out front with the 3. A squared is not a perfect cube, that stays in. And b squared, also not a perfect cube, that stays in. So from the start, the cube root of negative 81 a to the 5th b squared equals, oops, I didn't circle this part with it, negative 3a times the cube root of 3a squared b squared. So that concludes this video on simplifying radicals. Now, just so you know the purpose behind this and where this is going, the reason why we do this is because in later, basically the next video, but also just any other later topics, you're going to need to simplify radicals down as much as possible, because the next step is going to be adding and subtracting radicals that come in various forms. And once you're able to reduce radicals down, you may find radicals that are alike, and then you can combine like radicals the way that you combine like terms. So we're going to cover that in the next video. So thanks for watching, and see you in the next video.